In this video, we're going to continue our notes and examples on section 3.1, the definite integral. So let's look here at example 2. Now we're told for each problem, approximate the area under the curve over the given interval using 4 right endpoint rectangles. You may use the provided graph to sketch the curve and rectangles. So to get started here, let's go ahead and just sketch what the curve of this function looks like. So we see that our x term is squared. So that means we have a quadratic function here. So our curve looks like a parabola, like this. And now can we tell if our parabola is facing up or down? Given this negative out front of the x squared, we know that we are facing down. So to draw this graph, let's first find the vertex. So recall the vertex formula for the x value is negative b over 2a. And then we plug in this negative b over 2a into our function to find the y value of the vertex. So for us, x would be negative, well, b in this case is 0 because we have no x term. So we would just have negative 0 over 2 times negative 1, which is just 0. So the vertex itself has an x input value of 0. So then what's the output value, or the y coordinate of that vertex would be negative 0 squared plus 11. So that would just be 11. So our vertex here is equal to 0, 11. So let's go ahead and plot that. So we find 0, up 11. And so now we can start getting some more points here. So I could plug in when x is 1. What is the output value? So I could plug in y equals negative 1 squared plus 11. So that becomes negative 1 squared, which is negative 1 plus 11, which is 10. So I know 110 is also a point. We can do this with one more number, maybe input of 2. So y equals negative 2 squared plus 11. Notice this squared is just on the x, not the negative. So this just becomes negative 4 plus 11, which is 7. So we have 3 points here that we can plot on our graph. We have over 1, up 10, and then 2, up 7. And so this is a graph of a parabola, so we're symmetric about that vertex here. So I can just infer the points that I have on the left here would be at 10 and 7. And we can do this one more time just to get a really good sense of the shape here. So if we input 3 into our function, our output value would be negative 3 squared plus 11, which is negative 9 plus 11, which becomes 2. So at 3, our output is 2. Furthermore, then at negative 3, our output is also 2. And then we can draw our curve here by just tracing our parabola over those points. Okay, so there's what an image of our function looks like. Our function y equals negative x squared plus 11. So now let's get a sense of the area that we want to compute. So we want to compute the area over the interval from negative 1 to 3. So we can identify negative 1 here, 2, 3. So we want to approximate the area under the curve over this interval. So to get started, we need to determine the width of our rectangles. So for us, recall that width is going to be b minus a over n. Our a is negative 1, our b is 3. So our width is going to be 3 minus negative 1. And we want a total of 4 rectangles. So that becomes 3 minus negative 1 is just 3 plus 1 over 4, which 4 over 4, which is just 1. Then we see here that our interval, this negative 1 to 3, has a length of 1, 2, 3, 4. So then each chunk or each change, each unit is going to be a rectangle. And how is this problem different than the problem that we looked at in the previous video? Well, for us, I'll leave this change of x here equals 1. For us, here we want to find the endpoint rectangles. So that means we want to find the area of the rectangles formed by using the right endpoint of the rectangle. So let's first draw those rectangles in. So how high am I going to draw the first rectangle? Well, for the first rectangle, I'm going to go as high as that right endpoint. We're going to go all the way up here. Next rectangle will go all the way up to here, up to here, and etc. And fortunately for us, we already found those points that determine those right endpoints. So we're going to be able to compute the area quite quickly. So just to recall the image that we should be looking at, so the area of the rectangle is going to be the change, or the change of x, or the width of our rectangle, times the function value computed at that right endpoint. So let's make a chart like we did in the previous example. So we're going to input the x, the endpoint. So I'll call it x sub right endpoint, just so it's really clear what we're finding for our x, or our input value here. Then here we'll do the area, which again is change of x times f at x sub right endpoint. All right. So at this point, please pause the video and see if you can fill in those right endpoints on your own. And when you're ready, let's check together. All right, so we're using that right endpoint. So our first value that we're going to plug in would be 0, because 0 is the right endpoint of our first rectangle. So we're going to have 0, and what would come next? 1, 2, then 3. So our width is always 1 here as well, so we can just fill in 1, 1, 1. And then we can just read off from our graph and that work that we already did of what the height of our rectangles are going to be. So for that first rectangle, when we plugged in 0 here into our function, we got an output of 11. So that first height is 11. The next height, or the rectangle, the next height, the height of the next rectangle rather, is at 10. So we have 10 here. When we plugged in 2, we had an output of 7. So we should get 7 as the next height. And then finally, if we input 3, our output was 2. So the final height is 2. So the areas just become 11, 10, 7, and 2. And now what's the next step for estimating the entire area? Is to add these up. So if we add them up, we can count up here. So we have 10 plus 10 would be 20. And then we have another 7, 8, 9, 10. So 7, 8, 9, 10 coming from the ones, and then 2 10s here. So it'd be a total of 30 units squared. So then we could say, in summary, the area of the right endpoint rectangles is 30 units squared. In this video, we continue our work in section 3.1 using the definite integral. And we're now going to summarize 2 main definitions that we will see again in this course. So first, Riemann sums. So Riemann is a famous mathematician that came up with a way of estimating the area under a curve by using rectangles. So that work that we already did in examples 1 and 2 are examples of computing Riemann sums. So let's summarize that work here. So a Riemann sum is the sum of the areas of a certain number of rectangles that approximate the area under a curve. So we could say, let's take it off a shape again. So you'd say the sum of the areas under n rectangles that approximates the area under a curve. And we always want to give the area that we're looking at bounds. So we'll say a curve on A to B. So some more notation here. So if we look at the curve of the function f of x, then we denote change of x or delta x as the width of those rectangles. We compute change of x by computing b minus a, so the length of the interval, over n, the number of rectangles we want. So then the Riemann sum looks like the following. Rather, before drawing that out, I'm just going to draw a picture of what we should have in our heads here. So we're looking at a graph of f. We're looking at our interval from A to B. And we want to chunk up our interval into rectangles and compute the area by computing the area of those rectangles. So again, in the previous videos, we looked at a specific method for creating those rectangles, but in general, a Riemann sum doesn't specify the method. So what we were looking at before were Riemann sums with left endpoint rectangles or with right endpoint rectangles. But in general, a Riemann sum is just a way of computing or estimating area by chunking up what we want into rectangles. So then to finish here, we'd say the Riemann sum for the area under f of x on A to B is the following. So let's call the values on our x, on our horizontal axis, our x-axis, x sub 1, x sub 2, x sub 3, x sub 4. So we look at then, so then repeat sum, we would look at the sum to be the addition of all of the areas of those rectangles. So it would look like change of x times f of x sub 1 plus change of x times f of x sub 2 plus all the way up until change of x times f of x sub n. Now, there's a bit of notation that we often use to represent a sum where the terms are very predictable. So we see that we can predict the terms in this sum. Why? Well, what do they look like? They look like a change of x times f of x sub something. So I'll just put in a little I here. And now if we want to talk about all of those terms, what we can do is write this big sigma. So this is a Greek letter sigma, capital. And it's often used to denote such a sum. And we also decorate this sigma with our indices. So I, which is here, would start at 1 in our case and go all the way up to n. So if we wanted to write this sum out in a more succinct way, we could write it as the sum from little I going from 1 to n of change of x times f of x sub I. So this is often called summation notation. And again, it's just helpful when you have a large sum like this to write that sum more succinctly like this. So again, these Riemann sums are ways to approximate area under a curve by using chunks. These chunks are rectangles. But we will be learning about another way to actually find the exact area under curves. And that exact area is often called the definite integral. So the definite integral looks like the following notation. We have this soft, long, lazy s of f of x. We say dx from a to b. So just a bit of wording here on the notation. These a's and b's are called the limits of integration. This f of x here is the function we are integrating over. Which means the function we're finding the area under. And then this d of x tells us the variable that we are integrating with respect to. So before I write anything down, just referring back to that Riemann sum. So because we're looking at changes in x as our width, this, if we wanted to describe the area under this curve, we would use dx. So it tells us about which variable we are finding width of, or rather that we are chopping up our area under. So in words, I'll say the variable integrating over. So what is this amount? Well, or this whole object that I just wrote down? Well, this is a number when we have these limits of integration, and it's equal to the exact area under the curve of f of x from a to b. And so again, that's the picture we should have in our head, is a picture of our function f. So it looks like this, our a and our b. And because we have a dx here, we're looking at these slices coming as vertical lines on the perpendicular to the x-axis. So we're cutting the x-axis apart to get our chunk here. And then the exact area is a number that is equal to this entire term. All right, so we will be learning more techniques about how to find those numbers or those definite integrals exactly.